Hi everyone, welcome to Anthony's Hobby Corner. I hope you are all keeping well. And today I decided to add a quick video on how to add LED lighting to your passenger cars. Now, many of you may have passenger cars that are currently already pre-lit, perhaps with those filament bulbs in the older passenger cars. And so this will be a good opportunity and an avenue to convert them to having LED lighting. And for those of you who want to add some lighting to your passenger cars, well, here's a good opportunity to take a look at how it could be done. So this will more than likely be a two-part video, where in this video today I'm going to be showing you the thought process and perhaps the components and the circuitry on how to do this. On the next video I will be going through a live demo where I actually will build the circuit and put one into a passenger car, and we can see how that process goes as well. Okay, so before we dive into components and circuits and etc., let's just recap as to what we're looking to achieve here by converting or adding LED illumination into your passenger cars or rolling stock. So number one, we want to make sure that any kind of lighting that you put into your passenger cars will illuminate if it travels in both directions. And so if your locomotive is moving forward or reverse, you want to make sure that your passenger cars still remain illuminated. And number two, you also want to make sure that the brightness of the illumination inside your passenger cars remains constant no matter what speed you run your locomotives at. And that's really a bit more prototypical as opposed to some of the older filament bulbs that you have on passenger cars. They tend to vary in brightness based on the speed that you run your locomotive. And number three, we also want to make sure that the lighting inside your passenger cars remain constant and flicker free as they traverse over dirty track or even some of the insulated points on your switches and turnouts. And so that also adds a lot more realism to your layout. And of course, number four, the most important piece here is you want to make sure that your rolling stock can be run on any type of layout. So you want to make sure that these newly illuminated passenger cars will be able to run on any type of current, be it DC current layouts or AC layouts as in Markland, or even your DCC layouts as well. Alright, so let's just talk about some of the properties of an LED. An LED basically is a light emitting diode, and therefore it will exhibit the characteristics of a diode. So an LED, unlike a regular filament bulb, requires to be energized in a specific polarity, in the sense that you have to feed positive to the anode and negative to the cathode for it to illuminate. If you were to mistakenly invert those terminals and feed positive to the cathode and negative to the anode, it will not illuminate. And so also with regards to an LED, there's another interesting property in the sense that it is a current drain, or it is a current device. And what I mean by that is that it will consume as much current as you give it. An LED is not really more concerned about voltage but more about current. So we have to be careful to make sure that we only feed it the appropriate amount of current it should receive in order to be able to function normally. If it was to exceed the nominal operating current, it will actually eventually burn out. And therefore we need to make sure that we keep the current at the right levels. And so we have to put a control mechanism in place as we use LEDs anywhere. Now the typical LEDs that we use in model trains are obviously smaller form factor, and they also typically use the warm white LEDs so that you have better representation of proper illumination inside a passenger car. And so, given those criteria, a typical current for your LEDs will roughly be between 15 and 20 milliamperes. And the typical operating voltage for them, or the forward voltage for them, is about 1.8 to 2.5 volts. So let's just keep those two in mind as we go into the circuit elements of this design. Okay, now that we talked about our objectives and the properties of an LED, let's just go about and see how we go about doing this and building ourselves a circuit that would meet all the objectives we've actually listed above. So on this slide, you'll actually see the process we go through to make sure we have a happily functioning LED in your passenger car. So the first step, as you can see here, is we need to make sure that we can take any kind of track power or track current, be it a DC track current or an AC layout, as in Marklands, etc., or 3-rail Marklands, or even a DCC layout. We want to make sure that your passenger cars will be able to illuminate on any of these type of layouts. So the first step is to make sure that you take any of these type of currents and you convert it into a single direct DC direct current. And so the first step is to put it through some kind of conversion process. Once you convert that into a fixed polarity or DC signal, now the next step we need to do is we need to make sure we actually accumulate some of that power inside the passenger car. And the purpose of doing this is to avoid any kind of flickering that would take place as the passenger cars run on some perhaps dirty rails, or even they travel through some of those insulated spots on your switches and turnouts. So first we actually convert any kind of signal current into a fixed polarity DC signal, and then we take that current and we build a little reservoir inside the passenger car. At the same time, now that we've done that, you'll now have a fixed polarity DC plus some power reserve that's saved up in your passenger car. Now what we do next is we actually put it through a little bit of a regulator. We need to make sure we control the amount of current that comes out of this system and just deliver the exact amount that's required for your LEDs. And once you do that, you can feed that controlled regulated power that has some power reserve now and also has a fixed polarity into your LEDs. And this really is the process we're going to go through in building this circuit. Alright, so here in this slide you're going to see the components and the symbols that go along with each of these different stages of the circuit that we're going to build. So as you can see, the component that we use to convert direct current, or actually even a alternating current and any kind of DCC signal, DCC current, over to a single polarity is we use a component called a bridge rectifier. A bridge rectifier is nothing more than 4 diodes connected in a very specific orientation. And so what this does is it'll take any kind of current and convert that to a single polarity coming out. Then we feed that into our little power reserve. And the power reserve really is, in electronic terms, really is a capacitor. And a capacitor will actually hold some charge for you based on the value of the capacitor and the drain that you would take out, consume from it for a short duration of time. And then we feed that into some kind of a regulating mechanism. Now there are 3 methods you can use here, and perhaps you can I can refer you to another video I already have shot before that talks about these 3 mechanisms and the advantages of them and the disadvantages of each of them as well. So if you want to go into in-depth as to which one is better for you, you can actually take a look at that video as well. But for now, I'll just refer to a very high level. You can actually use a resistor. It's the most simplest mechanism. to regulate the current going into an LED, or you can use a very modern device called a LED driver, which is the CL2N3, that was designed just to drive LEDs and control the current going into an LED. Or you can use a current source like an LM334, which is designed to feed a specific amount of current at its output pin. Now, all these three mechanisms are actually very, very effective, and my personal favorite really is using either the CL2N3 or the LM334. And why do I like doing that is because both those mechanisms will maintain a constant brightness no matter what the track voltage would be. And of course, on the most right of the diagram, you'll see your LEDs, and of course there's a symbol for the LED. Okay, so I hope the analogy actually helped you understand the process we go through into designing a simple circuit for lighting your LEDs in the passenger car. Alright, so now let's go right into the weeds here and let's look at the actual circuit. It's actually very, very simple, but I felt that there was value in sharing with you the analogies first so that you can actually understand why these components are actually used and how they are used. So as you can see, we've got your input into the circuit, which is actually a DC or AC or DCC voltage, track voltage coming in, and that connects into a bridge rectifier. And the one rectifier that I'm using here is an MB2S type, which is basically the parameters you're looking for really is the forward voltage about 1 volt, and the current it can handle is about 0.5 amps, which is more than ample for a passenger car. In fact, you can actually even go much smaller, but I couldn't find one that was smaller than this. And by the way, this particular bridge rectifier that I'm referring to is a very small form factor. It's less than maybe half a centimeter in size. And of course, the voltage that this rectifier can handle is about 200 volts. Again, a way overkill, but it'll work very well for this purpose. Okay, so now that we have a constant fixed polarity coming out of the bridge rectifier, we can now feed all that power into a little reservoir that will now accumulate some power for us. And that will be done by the means of a electrolytic capacitor. And again, just as a reminder, the purpose of having a reservoir or a capacitor is to make sure that whenever your passenger car goes over any dirty track or goes over an insulated section in your turnout or point or switch, it will not flicker or lose intensity. Now you'll see here that I've put in a range of values for the capacitor, and this really comes down to a trial and error really for your own taste, in the sense that the larger the capacitor value that you pick, the larger the size of the capacitor. And so you want to make sure that you don't pick a capacitor too big, which will then not fit inside your passenger car. Now, if you're actually running an 8-hole layout, well, then most capacitors will fit inside there, no issues whatsoever. I would recommend looking at a capacitor between 470 microfarads all the way up to maybe 1000 microfarads, where the latter will give you far more sustained illumination during a interruption of power coming into your passenger car. So I would suggest that you experiment a bit and figure out which value works best for you. Okay, so now that we've accumulated some power into our reservoir or capacitor, next is to feed that into the current regulating device. And so you'll see actually I have 3 options outlined here, and you can actually use any one of those 3 options and they work pretty much equally well. The resistor obviously has a little bit of a drawback in the sense that it will actually dim as the voltage varies on your track. Not as noticeable at the higher voltages, but it is noticeable when you're actually running it at a lower voltage. Okay, so now let's talk about the second option here, which is using a LM334 linear IC. Now this one is a variable current source, and it has 3 pins, a V+, a V-, and an R pin. And basically it's very simple to utilize. As you can see here, the V+ connects to your positive of the capacitor, and the R connects to the V- through a 4.7 ohm resistor, which then feeds your LED. And what this does is that it makes sure that no matter what the voltage is, above I think about 3.5 to 4 volts, about 3.5 volts, it will make sure that your LED is going to have a constant brightness, no matter how much faster or slower you run your train or your locomotive. So that's one of the great benefits of using these type of chips or devices, because they actually provide you with the appropriate current and the functionality that permits you to have a bit more realistic operating session on your layout, because you actually have lighting now in your passenger cars that remain lit at a constant brightness, no matter how fast your train is going. So the way the LM334 has been configured here with the 4.7 ohm resistor, we're actually maxing that current source chip out a bit, and we're delivering 15 milliamperes to the LED. The LM334, I believe, is designed to deliver 10 milliamperes, but there's another additional current that comes across to the resistor into the LED as well. Now all of this is explained in my other video that I'm showing a link to here as well. You can actually review that video if you're interested in understanding how the LM334 works for this option. Alright, and so the last option we have here for a method of regulating power to your LED is using one of the more newer devices on the market, and that's called a CL2 device. In this case, it's a CL2N3, and these are called LED drivers. This device has been manufactured for the sole purpose of driving an LED, and therefore they function very well and are very simple to use. Even though this one actually has 3 pins on it, you only end up using 2 pins. They're both end pins, and the center pin is not connected. So the VA pin on the CL2N3 connects to your source, which is the capacitor and the bridge rectifier, and the VB pin connects to your LED, and that's it. And you don't have to worry about the input voltages or anything from that sort. It will make sure that no matter what the input voltage is, I think up to 90 volts, it will make sure that your LED only receives 20 milliamperes of current on the output end. And so they're very easy to use, very minimal thinking or calculations required, and they also function very well. They will maintain a constant brightness or illumination from your LEDs no matter what speed your locomotive or train is running at. The only issue here, and I've talked to this in depth, is that the start-off voltage for the CL2N3 ends up being about 4 volts, which really is not an issue, because most locomotives, as you start them up and they start to move, they already past the 4 volt mark anyways. So again, all that detail is shared on the other video. Alright, so now you have 3 options on how you can regulate your power. All 3 of them work equally fine. If you're looking for the most simplest way of doing it, obviously you can use the 1 kilo ohm resistor with the LED, and that actually works equally well. I mean, the differences are very minor. Because I actually have access to the LM334 and the CL2N3, I prefer to use them, but if you don't have access to them, a simple 1 kilo ohm resistor works equally well. Okay, so you're probably wondering, or probably have this question in your mind, is that, well, all these 3 mechanisms only talk about illuminating 1 LED. Well, in your passenger cars, you're going to probably have far more than 1 LED, so how do we handle that? So that's what we're going to talk about next. Now, before we go there though, I'd like to also indicate that I'm not a big fan of using those strip LEDs that come in a roll. Those actually called SMD LEDs. And the reason why is because people usually will cut a strip of them and glue it onto the top of the roof of the passenger car and then illuminate them with some kind of a driver circuit like this. But the problem is then you have about 10 odd LEDs inside your car, a passenger car, that looks extremely artificial and it's way too bright. And further, your capacitor now won't be able to retain enough power to drive all those 10 or 12 LEDs running at the same time, should your passenger car encounter an interruption of power, maybe going over some dirty track or insulated section on your turnout. So that's why I don't like to put a lot of LEDs inside a passenger car, because I want to get that fine balance between sufficient power reserve in the car with the capacitor, such that that the passenger car can actually go through some over dirty track and have no issues. And I also want to make sure that the brightness inside that passenger car is somewhat prototypical, right? So you have a few LEDs, maybe 3 of them at max, one on each end perhaps, or close to the ends, and one in the center or something like that, where you evenly distribute the illumination and make sure it's a bit more prototypical. And maybe 3 LEDs won't show up that much power anyways, about maybe 60 milliamperes at max, or maybe 45 milliamperes, and your capacitor will be able to easily drive those during a power interruption, a momentary power interruption on your track. Okay, so let's now talk about the first method, which is the using resistors to control the current going into your LED. And let's see how we can leverage that method for using multiple LEDs. So as you can see, the recommended method here that I'm showing you at the top is to have a single resistor for each LED. This is also the safest, because that way there is individual control for your LEDs. Remember, these things are not all perfect. They also function, may not practically function as designed theoretically. So in any ways, using an individual resistor for each LED it will give you a low activation voltage, in the sense that when the track voltage reaches about 4 volts, all the LEDs will start to illuminate at almost full brightness. And so, of course, this means you're adding a resistor each time you have an LED. Now, this method is the most complicated out of the 3 methods, because it's kind of a bit more rudimentary method of doing things, and not the most efficient to begin with. So as you can see, there are 2 other options as well that you can also leverage when you want to add more LEDs using resistors, and I've indicated them here below as solution 2 and solution 3. But the drawback, as you can see, is that the more LEDs you put in series here with a resistor, the activation voltage for the lights to illuminate goes up, because now you need more voltage to drive those LEDs because they're in series. So solution number 2 puts 2 LEDs in parallel, and then one by itself. In that model, you can see the resistors required. I'm assuming a 16 volt track power at max. We can see the current draws about 40 milliamperes at max here. And why is it 40 milliamperes? Because the 2 LEDs, LED 0 and 1, will consume the same amount of current, which is about 20 milliamperes. And then the second LED will consume 20 milliamperes by itself. So that's for solution number 2. And of course, solution number 3 within using LEDs is you can have all 3 LEDs in series with each other. And in that case, the current draw is very minimal, it's 20 milliamperes, and so your capacitor will last much longer in your passenger car with regards to a longer duration of interrupted power. But the issue here then is that the required track voltage for the LEDs to illuminate, it's about 7.5 to about 8 volts. And these are all approximations, by the way. I've not practically tested them. So there really is no clear answer when you're using, there's no clear winner when you're using resistors, because as you can see, if you were to have an individual resistor for each LED, the activation voltage is much less. Within 4 volts on the track, you'll have illumination on your passenger cars, whereas you're going to have to put an individual resistor in front of each LED If you try to skimp out on that and have less resistors, going to the other extreme of solution 3, you'll need to have a much higher track voltage to be able to drive those LEDs. So there is drawbacks in each of these options here as well. All right, so let's move over to the more modern methods of actually controlling power to your LEDs. Okay, so here we are now talking about using the LM334 current source or variable current source IC. Now this one, again, you have multiple options. You can put each of these LM334s in front of an LED, and you'll have constant illumination no matter what the track power or track voltage is. And you'll also need about 4.5 volts for it to activate and have full bright illumination. So that's really ideal for your passenger cars, especially for HO. Most motors will need about minimum 4 volts or so to even start moving, and so the moment they start to move, you'll have full illumination on your passenger cars. And alternately as well, you can actually use a single LM334, as you can see on the right hand side, and actually cascade as many LEDs that you want in series. But the problem with that is that for every LED that you add in series, you will be increasing the required track voltage to be able to illuminate them. And this is just a practical aspect of having LEDs in series. So looking at the scenario on the right, if you were to have 3 LEDs in series in front of one LM334, and they will all illuminate equally bright, and you'll have no issues there. They'll also maintain a constant brightness no matter what the track voltage varies as well. But the only drawback here is that it would require at least about 7 volts to activate those LEDs. And as you can see, I've shown within brackets what consumes that voltage. You need about a 1 volt for the bridge rectifier, about 3 volts for the LED plus the LM334, and maybe additional 1.5 volts each for each additional LED that you actually have in series. Now, to share a little bit of information about an LM334 before we move to the next option here, is that the LM334 will give you a constant current configured in this manner of about 15 milliamperes. They're designed to give 10 milliamperes, but the way, if you configure it this way, you can get about 15 milliamperes out of it. But it'll give you 15 milliamperes out, providing that it has an operating voltage of minimum of 1 volt, and it can go all the way up to 40 volts. So they're ideal for model trains, because most of your controllers are not going to go above 18 volts or even 20 volts at maximum. So no matter if you're running AC or DC or DCC, you're not going up to 40 volts. So these work ideally for model trains. Okay, so now we are at the final option here, which is using a CL2 type chip. It's a constant current LED driver made by a company called Microchip, and its sole purpose is to drive LEDs. And so on this option here, the CL2N3 model that I'm using is designed to drive 20 milliamperes out from its output pin, and so they are more than ample to illuminate any LED that you might have out there. The typical operating voltage of a CL2 type chip is about from 5 volts all the way up to 90 volts. So again, similar to the LM334, you have no fear about what voltage you're feeding at your track. It could be a Märklin AC system, it could be DCC, whichever you're having. You're not going to go up to 90 volts in any capacity. And at max, you're going up to about 18 volts, if at all. But not exceeding 20. So there's plenty of safe headroom on these chips again, if you're using them. I've purchased them from about 40 cents per piece, and so they're freely available as well from that standpoint. So there are multiple configurations here that you can use. I'm going to really show you 2 options here. Is that a CL2N3, you can actually have 1 again per LED, and if you're doing so, it will provide 20 milliamperes to your LED. And therefore the required track voltage for the LED to have full illumination is about 5 volts, which again is quite decent because your locomotives tend to start moving around the 4 to 5 volt range anyways, so you'll have full illumination as your locomotive starts to move. And again, these are very low current consumption type devices, and so your capacitor that you have that in the circuit will have ample power to drive these LEDs, providing you running over some dirty track, etc. Now on the right hand side, I've showed you another option where you can use a single CL2N3 to drive multiple LEDs. And in fact, you can keep adding on as many LEDs as you wish, because it'll just provide the 20 milliamperes through all these LEDs in series. However, the drawback, again, just similar to both the other options, is that for every additional LED that you add in series, the required track voltage for these LEDs to illuminate becomes higher. So as you can see, if you have 3 LEDs here in series with your CL2N3, you will need approximately 8 volts, I think, on the track to illuminate in full capacity or full brightness. Alright, so now we've gone through all 3 different options for powering multiple LEDs for your passenger cars, or even locomotives for that matter. Now, my personal preference really is to use either the LM334 or the CL2N3, primarily because they are very simple to use, there's no calculations required, and they provide constant lighting no matter what the input voltage is to your passenger cars, and that to me it's worth its weight in gold from that standpoint. With regards to resistors, obviously they also work fine. It's just that they're obviously cheaper to purchase and more freely available. It requires a little bit more calculations, but again, a viable option as well. It really comes down to personal preference. Alright, so this really is part 1 of a 2-part video series that I was planning on shooting. The first part here was to make sure I can take you through the journey of starting out from a very fundamental high-level position, talking about how we're going to go about doing this, and walking you through the process of going through the different elements that we're going to put together to build the circuit, all the way down to the weeds of the circuit diagram and the components, etc. So I hope you found that journey useful. It helps to bring you along and make sure you understand why we're doing what we're doing with regards to these components. In the part 2 of the video, I will be actually building this simple circuit. Most likely we'll be using an LM334 or a CL2N3. Just haven't made up my mind yet. And we'll be putting one of these in the passenger car and showing you how it works as well. So just stay tuned for that video as well. Alright, so I hope you found this useful. If you have any questions or thoughts, please don't hesitate to share them in the comment section of the video, and I'll be more than happy to respond. Thanks again.